La la la. I will begin with a river. Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. All right, let's get into it. So we were looking at the keyhole contour problem, and just remind you the setup here. We had 0, and then positive x-axis. And then what we're doing is we're surrounding 0 with sort of a keyhole, and then like that. And let's see here. So this has to go like a so, like a so, like a so, like a so. Then it turns in here, goes this way, that away, and that away, and that away back where we started. And so the indicated contour, I would say, it depends on epsilon and r. I don't have that in the notes, but it occurs to me that that would be a healthy addition to the notation to emphasize that there are two parameters for the contour here: the inner radius epsilon and the outer radius r. Right. So this point here, for example, is, it's kind of sort of, well, I guess it's debatable. It's approximately R0. It's not quite that, though, is it? And that's a weird way for me to write it. This is complex, right? So we should maybe say it's R plus, this is R plus, I don't know. Yeah, even that's quite, if you want me to be fussy, it is on the circle. So I should put the square root of r squared minus delta squared plus I delta to be fussy. Probably just have r. Yeah, but technically it's got to be on the circle, right? So if I have r plus delta, that's not, okay. But anyway, these kinds of nuances get washed away in the limit we're going to eventually consider, which is epsilon going to 0, of course, from the right, and r going to infinity. This is what we're after. And the reason we were looking at this is because we were looking at the function f of z equal to, what was it, z to the a over 1 plus z squared. Is that right? Yeah, where we mean in particular the e to the a logo log based at 0 of z. So we're talking about that particular branch cut of this function, and so that's holomorphic. F of z is holomorphic on this choice of domain. Well, that's not true. That's not true at all. Where does it fail to be holomorphic? At the singularity, which is where? Yeah, minus. So like this -1 over here, right? So to be fussy, I should say, with that point removed, right? In other words, f is meromorphic in this region. Okay, now, so we need to think about, like I said, we're going to integrate. So the big picture here is the integral over the boundary of this region of, f of z dz is equal to 2 pi I times the residue of f of z at the one singularity, which is, in fact, -1, right? And so that's going to be what? What's the residue? Looks like we should look at z to the a over what? Over 2z? 2 times 1 plus z, right? Evaluated at z equals to minus 1. Oh, I did that wrong, didn't I? I was trying to use the rule 4, but that's inappropriate. Why? I mean, the inappropriateness is manifest as I try to do this calculation, is it not? See what happens if you try to use the wrong rule? You get what? Division by 0, right? And not in a good way. So, yeah, so what should I do instead? Get the pole, it's a pole of order 2. We could use the, so let's do what? Do d squared, dz squared of, what is it? Oh. So it's just ddz of e to the, z to the a, right? No? Yes?
I guess technically you need, supposed to have the limit up front, but I don't think it really matters because you're just going to end up plugging in z equals minus 1 anyway. So.
Yeah, I think, but we derived something at the start of, maybe it was Monday, on the basis of the Cauchy integral formula. And so I think this one's okay because oh, I do have limit in the notes. You're right, Jonathan. So, I mean, where would that be an issue? That would be an issue if you had actually a 0 of order 3 downstairs and a 0 of order 1 upstairs or something. I mean, where would the limit matter in the calculation? I'm not sure. And yet that was one of the rules, right?
Yeah.
But
what we derived on Monday was that this would be the first derivative of z to the a.
Yeah, but
Divided by.
so what was that rule you're talking about? It was this, right? So I'm using this rule, which was, I think, an improvement on our previous limit rule. Although in my notes, I still got the limit there because I think I'm still working off the rules. But anyway, so it doesn't, I mean, we're not disagreeing. And then this is 2 pi I a z to the a minus 1 evaluated at z equals to minus 1, which is what? 2 pi I a minus 1 to the a minus 1. What's that? I don't know. What is minus 1? So I recast that as 2 pi I a e to the pi I to the a minus 1, and I get 2 pi I a e to the, what you got here, pi times a minus 1 I, which we could then rewrite as 2 pi I a cosine of pi times a minus 1 plus I times the sine of pi times a minus 1. Keep in mind, through all of this, a is a what? What was the fine print? There was some fine print about a at the start of this. A is between minus 1 and 1. That was given to us. And that will matter at some point. I don't think it matters at the moment that a is bounded between plus or minus 1. All I'm really using here, I think, is just that a is real, right? So in order to do Euler's formula and write this, I suppose even if a were complex, that would still be true, but then the fact that those are real and that this is a manifestly real expression, so I can read off the real and imaginary parts of this will be useful to us in a little bit, okay? So let's clean it up just a little bit more. What do we got? We have minus 2 pi a, the sine of pi times a minus 1, plus 2 pi a, the cosine of pi times a minus 1. All of that times an I, right? All right. So actually the residue here is kind of interesting. Now, next we're going to fuss about different pieces. And I connected the pieces last time for you guys, right? There's a gamma epsilon, there's a gamma r, the circle of, well, I say circle, but neither of these are quite, they're almost circles, right? They're nearly circles. And these are nearly line segments from 0 to r as well, but they're not quite that either, are they? So this is L plus, this is L minus. To be fussy, I suppose those also have an epsilon and an L dependence, right? So this point right here, if you wanted me to be technical and make a comment which doesn't really add anything, then this would be at, where would that be? Square root of what? Epsilon squared plus delta squared minus I delta. Yeah, I think that's right. Minus? Oh, minus delta squared, yeah. I know what you're talking about now. Okay, right. Okay, so the, so if you don't mind, I'm going to be a little bit sloppy here, as most people are, and just pretend like those are circles. Oh, actually, you tell me why this isn't bad. So suppose, you know, the modulus of f of z is less than m epsilon for some, you know, for z equal to epsilon. Then what can we say? The integral over gamma epsilon of f of z dz, right? Modulus of that is less than or equal to m epsilon, the length of gamma epsilon, right? But it's clear that the length of gamma epsilon is a little bit smaller than the full length of the circle of radius epsilon. So it's not really, the details of that don't really concern us, right? Because we have this inequality, which is all we're really after. 2 pi epsilon is the circumference, right? And then times my m epsilon. Now, what kind of bound? So the question then is, can we bound f of z on the inner circle, and how should we do that, right? So what does the inner circle look like? And z equals to epsilon e to the I theta, right? So what's f of z look like then? We've got what? We've got f of epsilon e to the I theta. How does that work out? 1 over 1 plus epsilon e to the I theta, quantity squared, and then times the exponential of a times log sub 0 of epsilon e to the I theta. We need to bound that thing. And let's see here. I have not gone into this level of detail in the notes. I basically just make a claim here. My claim in the notes is that the modulus of z to the a over 1 plus z quantity squared is less than or equal to the modulus of z to the a over 1 plus z modulus squared.
Oh yeah, so when I did this, I first showed, went to the side and showed the modulus of z to the a is equal to the modulus of z to the a, and then dealt with the denominator.
So that's something we can prove. Claim modulus of z to the a is equal to modulus of z to the a. Now that makes sense here because a is a real parameter, right? And then, okay, so then you can focus on the denominator. So let's make use of that claim. Let's see here. So I guess I don't really need. I'm getting too far into the weeds here, aren't I? So we should just consider. I mean, what I wrote there wasn't wrong. It just wasn't right. So let's look at z equal to epsilon. And then if we look at the modulus of f of z, that's equal to the modulus of z to the a over 1 plus z quantity squared. We trust Sam, who has told us that we can simplify the numerator as modulus of z to the a, and the denominator, well, right now I'm still working on equality here. But of course, the modulus of z is epsilon here, right? So, and then we need our handy dandy. This is less than or equal to what trick? This is the absolute value of 1 minus the 1 minus the modulus of z squared, right? So using that thing we keep doing when we have a sum of two things, we take the difference of their absolute values to make the denominator smaller and hence the fraction larger. Of course, that's still true if you square it. But then that's what we're looking at here. Now we're looking at epsilon to the a over 1 minus epsilon quantity squared. So there's our m sub epsilon. Let's see here. Yeah, I think I need that right here, right? No, right here. Now we're interested in the limit as epsilon goes to 0, so that's not a bad ask, is it? To have epsilon less than 1. It's a reasonable request for the calculation. And then, so what we have then, putting this together, is that the modulus of the integral over the gamma epsilon curve of f of z dz, right, is less than or equal to epsilon to the a power times 2 pi epsilon over 1 minus epsilon squared, right? And let's rewrite that as 2 pi epsilon to the a plus 1 over 1 minus epsilon squared. And the question is, what happens as epsilon goes to 0 for that? So I think we might as well do L'Hopital's rule, right? I mean, if you don't see it already, if we do L'Hopital's rule.
Or you go by
Substitution.
substitution, you don't get it. Oh, it's just by substituting epsilon equals 0. You get 0 to some positive.
Oh, yeah, I'm an idiot. That's not even, why am I doing L'Hopital's? That's not even 0 denominator. Not only can I not do L'Hopital's, I mustn't do L'Hopital's because it's not even valid, right? You got to be harder on me. Don't let me get away with that. Okay, so your point was the denominator is just 1 minus 0, which is equal to 1 when we think about epsilon going to 0, and the numerator is, so here's where we need minus 1 less than a less than 1, so 0 less than a plus 1 less than 2, right? And so that means we're looking at a to a positive power, and as epsilon goes to 0, that goes to 0, right? All right, so that takes care of the inner. Now we need to look at the outer loop, right? For z equal to r, greater than 1, I'm imagining, notice that we have modulus of f of z equal to the modulus of z to the a over, what was it? 1 minus z, no, 1 plus z. I guess it doesn't matter, does it? 1 plus z squared, right, which is equal to the modulus of z to the a by Sam's claim. And of course, that's equal to r to the a. And you put the inequality here, we're looking at 1 minus the modulus of z, right? Which is equal to r to the a over 1 minus r squared. Hence, the integral over the almost circle gamma r f of z dz, modulus of that thing is less than or equal to 2 pi r times r to the a over 1 minus r squared, right? Which is equal to 2 pi r to the a plus 1 over 1 minus r quantity squared. And let's see here. I mean, you might call this m sub r in the same way I called the other one m sub epsilon, you know? Now we need to think about the limit as r goes to infinity for that.
The trick of this one is that you actually, instead of doing r to the equals 1, you factor out 1 over r squared from the denominator.
Aha. So you say factor out a 1 over...
Or no, factor out r from that, and so then you get 1 over...
Factor out r from the denominator?
Yeah, so you get 1 over r minus 1. Although it should be r minus 1 because r squared is 1 rather than 1 minus 1. But it doesn't really.
I mean, this is negative, but we're squaring it. So if it's bothersome, we can go back to here and write r minus 1 everywhere. You know, it doesn't...
Oh, that's true.
It's since it's bothering you, how? I mean, I don't. We can agree to disagree. I mean, we can agree to agree here. Okay. Anyway, so the thing here clearly goes to 1. Yeah.
Why do you have to factor it out like that if you know that a plus 1 is strictly less than 2?
Yeah, I don't think there's much to show here. If you know that, right, exactly, a plus 1 is less than 2, that means that looking at leading coefficients, we're going to have that this goes to 0.
Do we immediately?
Well, a plus, I mean,
no, I see what you're saying.
that one's less than 2, this one's order 2, so the denominator wins.
Yeah. Well, I was just going by what you said. So then here you get r to the a minus 1 because the r squared cancels. Thing on the left.
So we have 2 pi r to the a minus 1 divided by 1 minus 1 over r. I mean, anyway,
But yeah, either way.
so then that is r to a, I guess I can rewrite this one more step. This is 2 pi over r to the 1 minus a times 1 minus 1 over r. I don't know, whatever floats your boat here. Anyway, the point is this goes to 0 as r goes to infinity, right? Because 1 minus a is what? If I look at this, this says that 1 minus a, well, 0 is less than 1 minus a, right? So we're looking at something which clearly goes to 1, something which is r to a positive power. So as r goes to infinity, this gets huge. And so we're looking at something that tends to 0. The reason I like this is you can kind of see more directly. It's, you know, potato, potato, whatever you like. But you can see that you need both a to be between 1 and minus 1, right? You can see from the r, we see why we need the upper bound, and from the epsilon, we see why we need the lower bound. But we need both to make both of these things happen. All right, then what's next? If you don't mind, I'm going to erase all this. Because the main point there was that those things go to 0. And so then we have is the integral over the boundary of this epsilon r region of f of z dz, the limit as epsilon goes to 0 and r goes to infinity, right, should be equal to just what? The integral along L plus of f of dz plus the integral along L minus of f of z dz. Let me write it this way instead, because this is kind of getting very cumbersome. Let me say as epsilon goes to 0 and r goes to infinity, we obtain in this limit, right? Then the question is, what is L plus, right? So let's try to be careful. What does L plus look like? And here's where I'm going to be actually slightly less than careful. So we say in the limit, this is equal to the integral of what? L plus goes basically from 0 to r, right? Well, I mean, I'll put the limit as r goes to infinity here just to make it a little bit more explicit. But we're looking at the integral from 0 to r, right? And then we have what? F of x dx, right? So we have x to the a dx over 1 plus x squared. Because up here, z to the a is just equal to x to the a up here. But down here, right, when you've got z is equal to x minus I delta, for delta, you know, very, very close to 0 and positive, you know, then the log sub 0 of such a z, it's equal to, you know, the it's equal to the natural log of the absolute value of, you know, x minus I delta, which I'm just going to write as x. And then what's the standard angle according to log sub 0 there? Well, plus 2 pi, excuse me, plus I times what? The angle as measured by log sub 0. What is the angle as measured by log sub 0 on the lower branch? It's 2 pi, right? That's why we have a 2 pi there. And so when you put that back up into here, what you have is that z to the a is equal to x to the a times e to the 2 pi ia for the lower half. And what's your dz? It's minus dx. Or you could say that, well, I don't know. How do you want to parameterize L minus is the question, all right? I'm saying that we can parameterize L minus by saying z is equal to x and, fine. Here, I'll do it less confusingly, or maybe more, I don't know. Good grief. Let's think of it this way. L minus is minus the reversal of L minus, right? I mean, oh, good grief. Words. Let me rewrite this as minus L minus. The reason for doing that is then minus L minus, the reversal of L minus has z equals to x, dz equal to, well, again, x, fine, x minus I delta, and dz equal to dx. So minus the integral from 0 to r of e to the 2 pi ia x to the a dx over 1 plus x, right? If you want to be really fussy, we are glossing over something here, right? But this is an allowed abuse in this course, okay? I have shown you the central, the heart of the calculation at least. And so that 2 pi ia is just a constant factor. It can be pulled out, right? And so what we're looking at is really 1 minus e to the 2 pi ia integral, assuming it exists, from 0 to infinity of x to the a dx over, well, I guess I don't have to assume it exists in this one. I think this proves that it does. And then you know that that is equal to, what's it equal to? Well, it's right here, right? So you can solve for the integral. Yeah.
You also need to say that delta goes to 0 in the precondition for that.
Yeah, delta going to 0 is, I would say, implicit within the epsilon going to 0. But yeah, fair enough. I wouldn't. What I'm trying to say is you really do need to think about the delta in order to get the angle straight. But that's really the only place that I need it for the calculation, right? I must be clear about the fact that the angle's 0 up here and the angle's 2 pi down there. Because that leads to, if you didn't pay attention to that, what would happen? You just get these things canceling out, right? Yeah, I mean, it would. But the whole point of the keyhole contour is to, what's the word? Treat the logarithmic jump carefully, right? Yes, Sam? Have it what?
Just the points where they intersect with the circles are like nice.
I don't know.
Have just those two angles go to 0 rather than the distance.
Huh. I left my computer on. YouTube goes wherever it goes, Let's see here. Stop. To be careful, you're saying maybe instead think about an angle going to 0?
Yeah, like rather than having those two lines be horizontal and have them like coming out from the origins,
But I can't get to the origin either.
well, no, but like.
Oh, like imagining, I know what you're saying. You're saying instead of the keyhole, like do something, I'll exaggerate what you're saying a lot. You're saying something like this.
Yeah.
And that.
Yeah, and then have like that data going to 0.
That's probably a good way to be more precise. And then rather than epsilon going to 0, you could say that the angle's going to 0. But, oh, but you also want to, I don't know. Anyway, I've shown you guys a way. I don't want to I don't want to ruin Sam's approach, yeah? Let's see here. So we were working through this one, right? So I think I hope you can understand the notes better after this discussion we've had. I mean, it took me an hour class time, give or take, well, 40 minutes, to kind of really work through it. So what, oh, I think so my idea to expand this out into sine and cosine was premature. I should have just left it. And then when we divide by the 1 minus 2 pi IA, then if you divide the top and the bottom by that, you get this, which is a sine of pi A. Of course, we knew, since A is a real thing and we're integrating from 1 to infinity, we would kind of hope that this definite but improper integral of a real quantity would be real. And as you can see, the answer is manifestly real there. So at this point, yeah, Gamelin remarks that the function g of w equal to 0 to infinity of x to the dw 1 plus x squared is analytic on the strip minus 1 less than the real part of w less than 1, as is the function pi w over sine pi w. Thus, by the identity principle, we find the integral identity holds. Isn't it the same thing? Oh, he's saying, oh, I get it. We have proved, right? It is saying something. I just am failing to see it. So we have proved that it holds here, right? But the function pi w over sine pi w, right, is holomorphic on the strip. I mean, it's got a 0 there, it's got a 0 pi, but on this strip, it's got no zeros. I mean, sine of pi has got no zeros except at integer multiples, except at integers. There's a pi w here, so that's not pi, it's 1. So the point is, because we've proved it on the real axis, then by the continuation theorems that I kind of butchered this semester, sorry, it extends. The singularity at 0 is removable. Well, I hesitate to, well, I'm not extending past the 0. I mean, we're just extending up and down off the.
This is 0 to, this should be negative 1 to 1.
Oh, have I misstated it? I was supposed to put minus 1 there. I'm sorry. But yes, you're right. In good point. It's because the 0, very good point, Sam. I'm supposed to have minus 1 here, and the 0, you're right, the 0 at w equals 0 is removable. What I was going to say is, right, that's a removal. So when we write this, it's with the understanding that this is defined to be 1 at w equal to 0. And so the argument we've just been through is for A on the real axis, right? We did the keyhole contour, which addresses A in that range. We found this formula. That formula matches a function which is holomorphic on the strip. Therefore, the formula extends to the whole strip, because the line segment from minus 1 to 1 certainly has a non-isolated point, right? So that's a nice argument. Here's another one. This one. You got it. Okay. Let's see here what we got. So let's see. This one, I look at z to the minus 1/2, and again, it's the same branch cut again. the same keyhole we did in the last example. You work through it, very similar argument. This time we got residues at plus or minus I, both of which are in the keyhole contour. So the residue theorem picks up two things, and you go through the calculation, and you can do this integral. Now, I don't know. Could we do this in calculus too? So now, to be fussy, I have not shown the fussy details of why, the given complex function, 1 over square root of z, well, z to the minus 1/2 over z squared plus 1, why the integrals corresponding to that on the inner and outer circles of the keyhole, why those vanish in the appropriate limits, right? So that detail's missing here. But that's one of the ways I can make these more reasonable test questions, right? As on occasion I may say, I might say, calculate this integral. You may assume that the uninteresting integrals integrate to 0 as appropriate. So, that's a dangerous game, because if you assume the wrong thing goes to 0, then you're kind of up a creek, right? But I don't know. So the next thing up is fractional residues. So here, I'll try to be brief, but it's very simple. If you only have the picture that's missing here is something like this. If you have a residue that's, say, on the edge, you imagine if the residue is like right on where you'd like to go. So suppose you're interested in really integrating like this, but you can't do that because x is a residue. Then what you do is you surround it with a little half loop, and then what ends up happening is it ends up picking up half of the residue. If you had a singularity on a quarter, on like a corner point, you pick up a quarter, and so forth. It's proportional to the angle that you subtend. So you notice when you go all the way around, alpha is 2 pi. So the usual 2 pi I is when you go all the way around the residue, but otherwise you just proportionally encircle. Isn't it? Yeah, and the proof is actually not bad. It's right there. Here's an example where that comes into play. If you wanted to integrate, z plus 1 times z minus I, you could use this modified half circle domain where you just like kind of half loop around the minus 1, use the fractional residue there, and that fractional residue, I only got pi instead of 2 pi, and there's a sign that matters. I'll try to talk more about this next class or something, but anyway, there's an example. Let's see here. We've already talked about principal values. Let's see here. Jordan's lemma is the only other thing really left. Yep.
Is there still a significant amount of research that's done to kind of find these nice contours? Or?
Finding nice contours to address a given integral is an art form. It gets worse. But this is Jordan's lemma. So that's a non-answer. It's kind of like, how do you parameterize a curve? It's a similar question. There's a creative process there, like imagining what you need to do. Jordan's lemma allows us to do integrals of sine and cosine that aren't quite supported by our previous inequality technology. So for example, integral of like sine x over x or cosine x over x become doable by Jordan's lemma, which gives us this inequality, which allows us to do the integral. On the next page, sine x over x is the main integral there. So, this one's got it's got the Jordan's lemma to bound the outside thing, and it's got the fractional residue there. So, I'll tell you what, next class I'll try to go through this example, but that's going to be pretty much it for this chapter. I don't really have much more to teach you in terms of residue calculus. I've kind of shown you the idea. The rest is up to you. You got a bunch of homework problems. I think after you do those, this will probably be your favorite thing to see on the final, honestly. They're relatively straightforward. But Anyway, I shut up. Have a good break. There is no help session today, right?